Okay, welcome back. So we're going to have a look at sine now. So sine was the one that we're interested in, and essentially using the same ideas that we used earlier, okay, for cos. That is, that we want to get used to that nomenclature because that's important, and we want to continue to analyse through the lens of exact values trig. So for our sine function, this is a bit more familiar for students, being able to see it this way. We can say that sine is got an equivalent. So that's the formal language. Okay, now this bit here will disappear for 0, and you'll just get sine of the argument. So the argument can be any thing at all, but what's the association for sine? You say, I know, y equals sine x, silly, but the association is y, isn't it? So when we look at our exact values triangle, the association is y. That's the one that we're. Okay, so we'll come back to that. But this means that when k is 0, k is an integer, k is 0, that 2 pi will be 0, and so it's just sine x. So sine x has this range. So we've got all the x's that can go in, backwards and forwards, or all the thetas, we'll call that theta as well. And for sine, it's between 1 and -1. So that's a typical range for our sine curve. So the x-intercepts occur when sine x is equal to 0. When is sine x equal to 0? Sine x is equal to 0, or sine theta is equal to 0, or sine r, or sine s, or sine t is equal to 0. When does that happen? Well, if we look at our particular association and exact values trig, what we'll get is, if we draw our 45-degree triangle this time, to be different, and we can count around in 45s then if we need to. That's something that we can do, just count around if we need to. And we could also do the negative version of that, but for the moment we'll just do this. And what we notice is that for the angle theta in this quadrant, the association tells us this is y, this is x, from our exact values trig triangle. It's an exact value triangle when the hypotenuse is 1. So what we can do is look for when is this y value 0. Y is 0 here, and y is also 0 here. Okay? So y is 0 when x is pi times k. So when x is, or theta, or x, or r, or t, or whatever, it doesn't matter, is equal to pi k, and k is 0, so our first one will be pi. If k is 0, our first one will be our first one will be 0, so this one. And then when k is 1, our second one will be here. K is 2 will bring us back 2 pi, there it is. K 3 pi, bring us back here. 4 pi, 5 pi, 6 pi, 7 pi, so on and so forth. So it'll always land in the right place for y being diminished to 0. When is it a maximum? Okay, so we've got half of our cycle there. So pi on 2 will be coincident with pi on 2. A value of 1, and that happens to be here. So half pi on 2. If we draw the diminished triangle on the axes, the diminished triangle has no x, but it does have y, and the y is now stretched all the way up to 1. So the maximum occurs there when x is pi on 2. Not only is it pi on 2, but if we go on the next rotation, we will get plus a 2 pi. And the way that we account for the 2 pi is we say k can be 0, -1, +1, etc. So we're taking into account plus and minus angles. So that's very interesting, isn't it? We can rotate around again in the cyclic one and go into the next cycle. So I'm not going to do a table for that one. The minimum is here, and this is 3 lots of pi. 3 lots of pi. So this is the negative one. So the y is here. The diminished triangle has a length on that side of y, which is -1, and that happens at 3 lots of pi on 2. Okay, so the textbooks draw it like that, don't they? But I try and get you to see there's 3 lots of pi on 2, counting around. But then we can rotate a whole cycle. So see how these are changing depending on the particular function. Okay, and remember that k, in all of these cases, k is an integer, so it's a whole number. And I just put them backwards because that's what you'll be doing in Maths 1. Okay, we do plus and minus for square roots and stuff, don't we? But today I'm being a bit annoying. Does it really matter? Well, it might. There's a couple of different ways to use that information when you do the topic that you'll be doing, and that's okay too. All right, so I could draw a table here and talk about, the only other thing I'll talk about is what happens when the exact value is not in a hypotenuse of 1, but r. How would we go about dealing with that? Well, then we can say that the opposite and the adjacent, okay? So we'd say the sine of theta this time wouldn't be just y, it'd be y over r. Okay, and this leads to this idea that y can be found by doing r sine theta. Now, if r is 1, y is sine. Ta-da! But if r is not, then we have to work it out. Alternatively, we could say that, how do we work theta out? Well, theta would be undo, wouldn't it? It would be the sine to the -1 of that ratio, y to the radius, whatever that was. So these things will crop up from time to time, having to solve for theta, or if theta is not an exact value. Okay, so we make the emphasis there, exact. Thank you very much. Not exact. So hopefully people don't get too excited about not exact, because it's not relevant to much of the harder maths in Maths 1, but it's there if you need to use it. All right, so we'll move on and do the next one, which is tan. Now, often these dimensions have domain and range restrictions. So if we just notice that before we start, the domain and range restrictions occur for tan. Okay, so tan, remember, is opposite over adjacent. So it's just looking at the y over the x. So if we put theta in there, tan theta is rise over run, isn't it? Tan theta is rise over run. Y is the rise over run. And we could do lots of different calculations there, but also we could write m. Tan theta is m. So we notice that the restriction in the domain is pi on 2 and multiples. Now look what it says here. Ooh. So this is asymptote. These are asymptotes. So this means that it's asymptotic to this point here. So if we were to extend it up and see this right in, very close, and then we were to think about what was going on there. So there we are, being Mr. Mathy, Miss Mathy people. Okay, and in our thought cloud, we would think infinitesimally, infinitely small. Infinitely small. Okay, infinitely small gap. And we got to use our insurance policy there to limit. And so it never actually takes the value on. Okay, so it's asymptotic. That we say that the tan is asymptotic at pi on 2 and minus pi on 2. They're just asym. P is silent. Asymptote. These are these red dashed lines. Okay, anytime we see that the limit idea in the insurance policy is going to be used, they're asymptotes. So tan can't take on those values, but it's okay if it's inside those values, and we can refer to it that way. Okay. So when is because it's a rise over the run, the tan is rise over run, and we can interchange x and any kind of variable, so I'm not bothered by that. Now, what's y? X sine. So sine and cos. So another way of writing this is writing sine. This often comes out in your work over cos theta. Okay, so in order for this thing to be 0, the numerator has to be 0, which means sine has to be 0. When is sine theta 0? Sine theta is 0 when sine theta is 0 when x is equal to Wrk. So sine again is the y. It's 0 here at pi and minus pi. It's also here. So any expression will be a multiple of that. 0 and 2 pi, or 0 and minus 2 pi, just to include our cousins. Okay, so we need to keep that into account. Now, when we do this, if I just do the diminishing triangles, just all over the place, because this is relevant, I mean, what's going to happen here? So we've got our y, so we've got a positive y and a positive x, so that means tan is positive in this part. Here we've got a negative x but a positive tan, so that means we're going to have a negative tan. Down here we've got two negatives, a negative y and a negative x, so that means tan is unexpectedly positive. And then down here we've got a positive x and a negative y, so we end up with negative. So it's just important to notice that, please, because that will come up. Okay? All right, so let's move on and let's think about the implication of changing the amplitude. So these are good ones. These are just saying, what happens if I change A? Now, A is, these bars mean magnitude, don't they? So the magnitude of A. Okay, so it's the amplitude. All right, so sketch y as cos x. Okay. No problem, right? Y is cos x. So there we go. Down, up. And change. 3 cos x. Oh, wow, that was 1. This will be 3. So it's going to be the same period and everything. It's just going to swoop down, and there'll be a minus 3 down here. Minus 3. It's going to swoop down in the same time. Whoosh. Okay, it's going to come down to this point in the same time. Whoosh. Back up in the same time. Whoosh. And then all the way back up to 1, 3 in the same time. 3. Whoosh. Okay, so that's our 1 and minus 1. And what about this one? Minus 3x. What goes on with a minus 3x? So minus 3x will be going in the opposite. So everywhere there's a 3, it's a minus. So it's going to swoop this direction. Okay, these are minus values, so they become positive values. Okay, and swooping down. And the reason I don't mind doing it by hand, imperfect, is because I'm trying to get you to build your own intuition. Or we could do a table and we could work it out and do all that silly stuff, but it's just as easy for you to do your exact values trick and think about it through that lens. Absolutely, absolutely valid. Okay? All right, so you can do your tables if you want to, or you can just use your intuition. All right, the next part is probably a more important part, so I might come back to the next video for this, because what we're talking about here now is the change in, oh, look, it's got a coefficient. Wow, so what does that do? What's the implication of that? So we need to understand that more clearly, and I'll come up to 15 minutes for the video, so I'm going to pause there, and I'll be back soon.